Hello, and welcome to the e-learning course, Introduction to the Intel FPGA F-Tile. FPGAs are popular because of their flexibility, supporting many different designs and applications. That flexibility invariably leads to complexity in certain device structures. In this case, the F-Tile and its transceivers. While the F-Tile architecture is complex, this training will show the major F-Tile components, how they work, and how they can be configured. This will help your understanding when you review the details found in F-Tile documentation. After attending this course, you will be able to describe the architecture and building blocks that make up the F-Tile. You will see the many options you have for configuring the blocks, whether you are implementing a standard protocol or implementing a custom interface. By understanding the F-Tile architecture, you will be able to choose the right configuration for your design needs. The F-Tile is Intel's latest high-speed networking and communications transceiver tile, following up and building on the features and support found on the prior E-Tile. With the F-Tile, you get up to 20 configurable transceivers. How many you can use depends on the data rates and features enabled. Data rates up to 32 gigabits per second NRZ and 116 gigabits per second PAM4. Ethernet support from 10 to 400G in the Ethernet standards shown on the slide. Ethernet support benefits from a full or partial hardened Ethernet stack in the F-Tile. PCI Express Gen 4 support up to by16. And support for a wide range of standard interfaces and protocols, including interlocking, CPRI, Fiber Channel, JESD, and DisplayPort. There is also flexibility in the tile for implementing your own custom protocol solution right alongside these standards, making use of the high-speed FPGA fabric architecture to which the tile is connected. Before we go further into the F-Tile, let's compare the F-Tile against some of the other transceiver tiles available from Intel FPGA today. In this table, you will see the names of each tile in the top row. This first row contains the number of channels and the maximum data rate specification for each tile. The final row contains some details on the hard IP protocols found on the tile. The tiles are organized into two groups on the slide. The first group on the left is network and communication tiles, made up of the F-Tile and the E-Tile. These are general-purpose tiles, and in addition to the hard IP shown in the table, these tiles support a wide range of protocols using soft IP. The second group on the right is processor-attached tiles, made up of the P-Tile and the R-Tile. These are not general-purpose tiles, as they are designed to support specific protocols. The P-Tile supports PCI Express, and the R-Tile supports PCI Express or CXL. The block diagram on the right of this slide shows the F-Tile, highlighting 4 of the 5 major block types found in the tile. PMA shown on the left. Protocol hard IP in the center. The embedded multi-die interface block or EMIB. And the clocking network along the bottom. The final block type, the reconfiguration architecture, is not shown as it will be covered in more detail in follow-up training to this one. Each of the 4 main blocks types will be covered in this training, focusing on features and supported configurations for each. This information is critical for success as you map the interfaces for your next FPGA design to the F-Tile. For our discussion, we start with a look at the transceivers in the PMA section. Then we will investigate the various hard IP solutions found in the F-Tile and their features. After that, we move to the EMIB, the connection from the F-Tile to the FPGA fabric die. Finally, we will see how all of this is supported by PLLs and clock routing in the clocking section. So, let us look at the PMA. So the F-Tile PMA has all of the features expected in Intel FPGA transceivers. There is signal conditioning control for improving signal integrity that can be set manually or automatically. There is support for both NRZ and PAM4 modulation, the same as on Intel FPGA E-Tiles. The PMA contains embedded PRBS logic for debugging. There are PLLs for generating clocks for TX operation and for recovering clocks during RX operation. The SerDes supports converting between serial and parallel data of different supported widths. and two types of bonding are supported. PMA bonding, which is used when a channel runs over 32 gigabits per second PAM4. And system bonding, which is used when in multi-lane protocols, where multiple lanes represent a single interface. There are two types of transceivers found in the F-Tile, the FHT PMA and the FGT PMA. FHT stands for F-Tile high-speed transceiver, while FGT stands for F-Tile general-purpose transceiver. There are 4 FHT PMAs per F-Tile. These connect solely to the 400G hard IP. Then there are 16 FGT PMAs per F-Tile. These connect to all hard IP blocks. Because of their design, the FHT PMAs support both NRZ and PAM4 in data rates from 24 to 116 gigabits per second and in the data rate bands shown on the left. The FGT PMAs support from 1 to 32 gigabits per second NRZ and 20 to 58.125 gigabits per second PAM4. Be aware of the following notes. The PMA data rate supported is always dictated by the data path clocking mode and PMA type you select. In any Agilex package, there will be maximum of 8 FHT PMAs in the package. This means that a maximum of 2 F-Tiles in the package will have their FHT PMAs bonded out. Finally, not all FGT PMAs support the same data rates, with the lowest 4 channels limited to a maximum of 32 gigabits per second. All 4 FHT PMAs are independent of each other, though they can be configured in multi-lane protocols. They connect only to the 400G hard IP. This slide shows the Ethernet, CEI, and other protocols they support. The 16 FGT PMAs are also independent of each other. They too can be configured for multi-lane interfaces. They are arranged in groups of 4 contiguous PMAs called quads. Being in quads means that there are certain resources that can be shared by the group. The quads are the basis for many multi-lane applications. The 16 FGT PMAs feed all hard IP in the F-Tile. Being the general-purpose transceivers, they support a much longer list of standards and protocols. Now let's talk about the hard IP. The F-Tile has 3 protocol IP: a 400G Ethernet, a 200G Ethernet, and a PCIe hard IP. This allows users to mix and match interfaces according to their needs. Within each hard IP, hardware blocks can be enabled or disabled according to how the IP are configured in software. This solution allows users to trade features for bandwidth, depending on which hard IP and the blocks within that are chosen. Each hard IP is logically divided into discrete paths, we call streams. These streams are indicated in each of the hard IP blocks in the diagram by the columns on the far left. Each stream represents the minimum unit or the smallest configuration supported by that hard IP. For both Ethernet hard IP, one stream supports 10 or 25G Ethernet. For the PCIe hard IP, one stream supports a by 4 implementation of a Gen 4, 3, 2, or 1 PCIe controller. Thus, the 400G hard IP has 16 streams, the 200G hard IP has 8 streams, and the PCIe hard IP has 4 streams. Each stream supports a maximum data width of 32. If more than 32 bits wide is needed to support the line rate, then multiple streams are needed. The PMA width also determines the number of streams used. Each PMA with a width of 32 or less uses 1 stream. Each PMA with a width of 64 uses 2 streams. Each PMA with a width of 128 uses 4 streams. So, for example, 10G Ethernet needs a single stream. 40G Ethernet, running on 410 gigabits per second PMAs, needs 4 streams. And 53 gigabits per second PAM4 requires a 64 PMA width, so it needs 2 streams. In order to support higher bandwidths and wider interfaces, streams are combined to form fractures. Fractures can contain 1, 2, 4, 8, or 16 streams. In effect, a single stream is equivalent to a by 1 fracture. In the diagram here, Fractures are shown by the remaining columns in the hard IP. As you move to the right, you can see that streams are combined to form by 2, 4, 8, and 16 interfaces. Let's look at some examples with the 400G hard IP. Here, a 50G Ethernet example is highlighted. Notice that 2 streams are used. As a result, any other hard IP configuration that would use those 2 streams is not available. Next, a 40G Ethernet or 100G Ethernet example is highlighted. Now, 4 streams are used. And again, any other hard IP configuration that would use one of the 4 streams is not available. Looking at the PCIe hard IP, the smallest unit is the 4-lane fracture. So for a by 8 PCIe interface, 2 streams are used. And for a by 16 interface, the entire PCIe hard IP is used. Just like the Ethernet hard IP, when a PCIe hard IP stream is used, other configurations that would use that stream are unavailable. Now let's focus on the individual hard IP. Both the 400G hard IP and the 200G hard IP support 10 to 200G Ethernet, along with related standards such as fiber channel. In addition, the 400G hard IP, of course, supports protocols beyond 200G. The big difference between the 2 hard IP is the presence of the MAC in the 400G hard IP. Both hard IP support auto-negotiation and link training used in KR interfaces, but PTP is only available with the 400G hard IP due to its inclusion of the MAC. Both KR and PTP utilize soft logic in the FPGA fabric. This table then shows on which hard IP they are supported and how F-Tile resources are used. Since the 400G hard IP is the only one with a MAC, the full Ethernet stack is only supported there. The 200G hard IP would require additional FPGA logic for MAC functionality. Hard IP modes define how they are fractured and determine the protocol and the number of PMA transceivers needed. There are 6 modes available shown in the table on this slide. The 6 modes are full hard IP, PCS Direct, Flexi, OTN, FEC Direct, and PMA Direct. Notice all modes use the PMA as that is the only way high-speed signals can enter or leave the tile. PMA Direct mode, unlike other modes, does not use the underlying logic of the fracture, the MAC, the PCS, or the FEC. It only uses the fracture's connections to the PMA. FEC mode uses the hard IP up to the FEC, but then skips the rest of the hard IP. PCS Direct mode uses up to the PCS, but skips the MAC if available in the tile. The FEC is optional in this mode. The remaining modes enable and disable hard IP features according to the standards for which the modes are named. The key here, again, is flexibility. Use the mode closest to your requirements to make use of as much of the hardened resources as you can, and use the FPGA fabric for the rest. There are 4 FEC cores in the 400G hard IP and 2 FEC cores in the 200G hard IP. The FEC cores can be split to support multiple independent streams. Each FEC core is connected to a select grouping of 4 streams. The number of streams used will determine how much of or how many FEC cores will be needed by a single interface. This slide shows the 4 different FEC modes supported in the F-Tile and their typical uses. Note the low latency FEC mode is a new mode supported by Intel FPGA, available on the F-Tile. Moving to PCIe, the PCIe hard IP contains 4 PCIe controllers. Each controller contains a fully functioning PCIe protocol stack of FiMac, data link, and transaction layers. Each controller connects to a common PCS and the FGT PMA for the complete protocol implementation. The hard IP supports initial lane configurations of by 16, 8, or 4. So in configuring the hard IP, you can have 1 by 16, 2 by 8, or 4 by 4 PCIe interfaces. This allows the hard IP to support bifurcation, which we will talk about in the next slide. As mentioned before, each controller supports Gen 4, 3, 2, or 1. They can be configured for root port or endpoint operation in the sizes as indicated in the table. Note endpoint and root port configurations require a different number of signals into the FPGA fabric. This means support for endpoint or root port changes with the number of ports implemented, as indicated in the table on the right. So, for example, the hard IP supports 2x4 root ports. If 2x4 endpoints are needed, then 2x8 ports must be configured and the remaining signals in each by 8 interface are unused. Bifurcation is also supported. Bifurcation, if supported by the system, allows a single physical PCIe port to be split and recognized by the system as multiple smaller individual ports. So each of the 4 controllers would be recognized by the system as a separate port connection, though they are actually using different lanes of the same physical connection. The hard IP also supports transaction layer bypass, which allows you to build your own transaction layer in the FPGA fabric to support features unsupported by the hard IP transaction layer. In our next section, we will move from the hard IP to the EMIB. Similar to other tiles, the EMIB is the connector between the F-Tile and the FPGA fabric. It is divided into 24 EMIB streams, with each mapping directly to a hard IP stream. And like the hard IP streams, EMIB streams are combined to support higher bandwidth interfaces. This diagram shows how the EMIB hard IP and PMA resources are mapped. The 400G hard IP, shown in gold, can access all PMA lanes and EMIB streams 6 to 23. The 200G hard IP, shown in blue, can access FGT PMA quads 0 and 1, the lowest 8 lanes. It can access EMIB streams 0 to 7. The PCIe hard IP, shown in purple, can access all FGT PMA lanes and all EMIB streams except 6 and 7. This information is very important when you are trying to build multiple interfaces inside one F-Tile. You must confirm you have the resources and connections needed to support the design. So, why are EMIB streams 6 and 7 singled out? These 2 streams are where IEEE 1588 Precision Time Protocol is implemented. PTP is used for time syncing in Ethernet connections and is only supported on the 400G hard IP because it has the MAC. So, if PTP is enabled, streams 6 and 7 are unavailable to the 200G hard IP, and a PCIe hard IP simply does not connect to them. Note, if PTP is enabled, all ports on the tile with PTP enabled will share those 2 streams for PTP. For our last look at F-Tile architecture, let's look at the clocking. Clocking is what makes everything happen, so understanding clocking options and rules is absolutely necessary for design success, especially the more of the F-Tile you want to use. The F-Tile has 3 types of PLLs to support clocking the various resources in the tile. First are the PLLs found in the FHT and FGT PMAs. Each PMA has a dedicated TX PLL and a dedicated RX CDR PLL to support the channels it drives. These PLLs are depicted by the graphic at the middle top. Second, all FHT PMAs share 2 common PLLs that are used to generate the 100 and 156.25 MHz reference clocks for them. Using separate PLLs in this way ensures the reference clocks for the high-speed channels are as clean as possible. Third are the system PLLs. Every F-Tile has 3 system PLLs for clocking the digital portion, the PCS, of each data path. With 3 system PLLs you can use, for example, 1 system PLL for PCIe and 2 for Ethernet and other protocols. Or you can use all 3 for various interfaces within the Ethernet and PMA direct digital blocks. Keep in mind, though, because there are only 3 system PLLs, multiple hard IPs with different line rates may have to share a system PLL. When this happens, we recommend using the hard IP with highest line rate to determine the system PLL frequency. The hard IPs with the lower line rates must be overclocked. All PLLs support fractional and integer modes to provide flexibility in the PLL multiplication factors needed to generate the required frequencies for the channels. To provide the clocks for the PLLs, there are 2 separate reference clock networks, one for the FHT PMAs, and another shared by the FGT PMA and the system PLLs. The FHT reference clock network contains two clock lines that provide either 100 MHz or 156.25 MHz clocks to all four FHT PMAs. These clock lines are driven by the two common PLLs. As you can see from the diagram, each PMA can select from either reference clock line from either PLL. Because the reference clock is required, at least one of these PLLs must be active. The two PLLs are connected to two reference clock pins on the FPGA. These two pins can be driven by frequencies from 100 to 200 MHz. The FGT and system PLL reference clock network is hierarchical, divided into three clock line types: global, regional, and local. Global clock lines, shown in the red, drive all FGT PMA and system PLLs. Regional clock lines, shown in yellow, drive two FGT quads and all three system PLLs. Local clock lines, shown in purple, each drive a single quad. For connecting source clocks, there are 10 reference clock pins on the FPGA. 4 connect to global lines, 4 connect to regional lines, and 2 each connect to a single local clock line. The 2 local reference clock pins are bidirectional to support protocols like CPRI. In addition, select unused TXV PLLs may also be used to generate reference clocks for neighboring channels. This is like older Intel FPGA transceiver architectures. So, what does this all mean? It just means you have lots of options. No matter which IP, the width of its interfaces, and the number of fractures you need, you have the clock pins and clock lines for them to use, individually or by sharing clock sources. System PLLs are the recommended way, in most F-Tile configurations, to clock the digital data path stream of a channel. This is similar to the channel PLL found in the older E-Tile, except the system PLL is a separate resource. When using the system PLL, the TX and RX CDR PLLs drive most of the PMA up to the PMA interfaces. These are shown in the orange and purple lines in the graphic. The system PLLs drive the PMA interfaces, the hard IP, the EMIB, and on into the FPGA fabric. Using the system PLL supports the maximum data rates of the F-Tile. PMA clocking mode is another data path clocking configuration. In this case, the PMA-generated clocks drive the PMA, the rest of the data path, and on into the FPGA. This clocking is like the transceiver clocking used in older Intel FPGA tiles like the L and H tiles, and in the transceivers in older FPGA families like the Intel Aria 10 FPGA. So, if designers have their own protocol solutions that make use of this clocking strategy, then they can continue it in the F-Tile if they wish. In particular, this clocking mode is an option when PMA direct mode is selected and the hard IP is bypassed. Note there are data rate limitations when this mode is used. This concludes our introduction to the Intel FPGA F-Tile. In the training, you have seen that the Intel FPGA F-Tile has the resources to implement a wide range of high-speed protocols, interfaces, and standards, and it provides flexibility to build your own custom interfaces as well. Pairing this with a high-performance FPGA fabric make a compelling solution for many applications and systems. Intel provides lots of documents to help get started with designing with the F-Tile. If you want to learn more details about many of the resources we learned today, then you can start with the F-Tile architecture and PMA and FEC DirectFi IP user guide. Then use the second link to find resources on specific F-Tile configurations and solutions. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5-minute quick videos, along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access many more e-learning courses just like this one. Lastly, you can also enroll in a live instructor-led course presented either in person or virtually over the web. All instructor-led courses have hands-on lab exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help support resources for you to access. This includes viewing and posting questions to the community forum, which is monitored by skilled Intel FPGA application engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. This concludes the introduction to the Intel FPGA F-Tile training. Thank you and have a good day.